So when you want, you can start. Thank you.
So good afternoon, everyone. Today I'm going to present on thermochromic materials and their applications in energy and environmental fields. So before going into the details of my presentations, I'd like to introduce myself briefly. I am Diptiman Dinda and I am from India, and I have done my PhD from Indian Association for the Cultivation of Science, that is in the eastern part of India in 2017. And this research institute is very famous or very old research institute, and I think it's one of the most oldest research institute in Asia. And this research institute is very famous for Professor C.V. Raman, who received a Nobel Prize for his groundbreaking works of Raman effect. And I am very privileged to be a part of this prestigious research institute. And after finishing my PhD from ICS, then I moved to Seoul, South Korea to continue my research works. And then I changed different institute there. And finally, I moved to Barcelona in 2023. And I joined in ICN2 to work as a senior postdoctoral researcher with Professor Daniel Ruiz in Nanospan Group. And mainly, I have expertise in designing different graphene-based nanomaterials, nanosheets, quantum dots, and making them optically active. And I have used them for different sensing and energy conversion applications. Also, I have the expertise to design plasmonic and graphene-based heterostructures. Now, I am in Nanospan Group is trying to develop some graphene-based thermochromic materials, which can be explored for the smart window applications. So today, I'm going to present the basics of the thermochromic materials and how they are behaving, and how we can design this kind of thermochromic materials, and how they can be applied in different field of applications, and how how the current scientific works is going on with thermochromic materials, and how people are using these kind of materials in smart window or anti-counterfeiting or thermal energy storage devices. And finally, I will briefly describe some of our research works in Nanospan Group exploring this kind of thermochromic materials. So this will be a little bit different from other presentations. I mostly will be focused on the basics of the thermochromism. So first, I start with what is chromogenic materials. So chromogenic materials are these types of materials which change their color with response to external stimuli. And if you look into the nature, then you can say there are different shades of sunlight which change with respect to atmosphere, and also different kind of organic dyes which also change their colors with respect to stimulations. And this kind of stimulation can be different types. It can be photo, it can be heat, it can be electric field or solvents. So different things it will be. And here I'm going to focus on the thermochromic materials. So thermochromism. So the phenomenon thermochromism is related with these thermochromic materials, which basically change their colors from colorless to color, or from one color to another color by applying heat. And it can be done reversibly or it can be done irreversibly. So it depending on the situations or depending on the materials, you can design this kind of reversible and irreversible thermochromic systems. If you look into the commercial markets, there are different types of shirts with the thermochromic logos. They are very reversible in nature, and depending on the outside and indoor room temperatures, they change their colors. And also in case of food packaging systems, also these are based on irreversible thermochromic systems, which will change their color from sorry, it will be better to do it with the laser printer. Okay, now it will be fine. So when they will be pressed, it will be green in color, and then when they will expose to the temperature, or their freshness will be lost, and it will change to orange or red color. So this type of packaging is based on the irreversible thermochromic systems. So which type of materials are responsible for this kind of thermochromic behaviors? If you look into the organic materials, there are three types of materials which shows this kind of thermochromic behavior. These are leucodyes, polymers, and liquid crystals. So if you see these leucodyes, actually they are furan or pyran based organic dyes, which have this closed chain, and if we put heat or other external stimulations, then they will open their form, and they will convert from colorless closed state to the colored open form. And depending on the environment, they will change their colors. And in case of polymers, depending on the environment, they also try to agglomerate, and they change their optical absorbance, and as a result, they change their colors. In case of liquid crystal, we know that liquid crystal have polar head and non-polar tails, so they can align with respect to the external stimuli, and when we apply heat, then this type of liquid crystals, they will arrange themselves, and as a result of it, there will be change in their refractive indexes, and ultimately they will change color. So with applying this kind of organic materials, you can design different thermochromic systems. So apart from organic, inorganic materials can also be explored for this purpose. There are many transition metal complexes like mercury iodide or copper silver mercury iodide. They mainly change their phases from alpha to beta phase with applying heat, and they change their color. Or if we can make different charge transfer complexes such as pyridine iodine complexes with coppers, then because of this charge transfer effect, they will change their absorption and eventually the color. Apart from these transition metal complexes, we have also semiconductor vanadium dioxide, which is very frequently used for this thermochromic, for developing thermochromic systems. They basically change from monoclinic to the rutile phase when we apply heat, and they change, and because of their changing from insulating to metallic phase, there will be change in their optical transmittance, resulting they show their thermochromic behavior. So this type of materials can be useful for this purpose. Now, the question will arise, how do they work? So if we want to design a reversible thermochromic systems, so we have to take care, or we have to mix three different types of component. One is leukodye. Earlier I already mentioned how they work, and another is phase change material, and the third one is the color developer. So if we mix these three together, then we can make a reversible thermochromic systems. Actually, this phase change material, which basically is a aliphatic acid or alcohol, they will change their phases from solid to liquid when we will apply heat, and they will, because of their phase changes, they will release energy, and that energy will be explored to stabilize the open form of the liquid dyes in addition to the color developer. So if we look after their mechanism, then in the solid state, actually, as the color developer and the dye are phase separated from the PCMs, they will try to agglomerate, and they will interact with each other to stabilize the open form of the liquid dyes, forming the color in the solid state. When we melt those PCMs, then because of the better dispersibility, then the color developer and dye will be dispersed in liquid phases of PCMs, and then there will be no interaction between the color developer and dyes. So now the closed form of the dye will be stabilized in the form of colorless states. So that's how we can design from color to colorless thermochromic systems. Those are working reversibly. When we heat the mixture, it will be transformed to the colorless state, and when we cool down, it will turn back to the colored one. So if we look into the literature, this type of reports are being done. So by tuning the PCMs and color developer and different type of dye, you can make different type of colors with these reversible thermochromic systems. Now, what will be the picture in case of irreversible thermochromic systems? So it can also be done organic with the organic molecules and inorganic molecules. In case of organic molecules, the diacetylene molecules are the best in this scenario. Actually, these diacetylene molecules form their polymer structures in presence of UV light, and they form a linear structures actually. And as a result of it, they will show blue or violet color depending on the groups beside these acetylene moieties. And when we apply heat, then their geometry will be changed, and they will convert themselves to stabilize their energy. So that's why the linear structure will be lost, and as a result of it, the conjugation will be lost. So there will be change in their absorption, and eventually they will show different color. And as they don't allow to return back to their initial stage, which is not energetically stabilized, so these molecules shows irreversible thermochromic systems, thermochromic behaviors. And with inorganic complexes also, we can design this kind of irreversible systems. If we heat ammonium manganese pyrophosphates, and if we heat them, they will lose nitrogen and moistures, and they will convert to their oxide forms, and eventually the violet or blue color compound will be turned to colorless states. So, by applying this kind of organic complexes, we can design irreversible thermochromic systems. There are also different complexes like nickel oxalate, cobalt oxalate, or copper isothiocyanate, which also shows this kind of irreversible thermochromic systems. So now, how they can be explored. So if we look into the consumer products, then you can see in the markets, you can see thermochromic mugs, thermochromic bottles, or T-shirts are available. If we can put some or design this kind of thermochromic materials over these mugs or bottles, then depending on the hot or cold state of the liquid inside those mugs or bottles, they will change their color, and we can easily determine the states of the liquids inside those bottles. So these are very attractive to the people. And not only the mugs, the t-shirts, we can put this kind of thermochromic logos inside over the t-shirt, and they will change their color depending on the outdoor or indoor temperatures. And for the people who are work out every day, they can also wear this kind of thermochromic shirts, which will change their color depending on the body temperature of the person. So this kind of products are very popular in the market. Apart from these commercial product, industry nowadays are also using these thermochromic materials, especially in case of food packaging, or the food is exposed to temperature or not. These kind of things can be explored with thermochromic materials. Recently in Turkey, we all know that Coca-Cola bring this kind of thermochromic materials or commercialize to make some logos over their cans, which will change from colorless to color when they will become they will chilled in that condition. They will be colored, and when they will be in normal room temperature, they will be colorless. So this type of with these reversible thermochromic systems, they try to explore the markets. And not only with the reversible, but also with the irreversible thermochromic systems, we can the people are using them to improve the quality of the food packaging, and to enhance the quality of the foods available in the supermarkets. So apart from these, also people are using this kind of thermochromic materials for biomedical applications, especially with the irreversible thermochromic systems, to know the condition of the vaccines or valuable injections, or even surgical instrument, whether they already are in good condition or not. And so depending on the color changes, we can easily know about their current conditions. So this kind of irreversible thermochromic materials are very useful for biomedical applications. Apart from the instruments, also this kind of thermochromic materials will be effective for drug delivery systems. There are few reports where the polymeric thermochromic chains are attached with the drugs. They basically makes same assembled structures, and when we hit those polymers, then because of the change in their transmittance, so they will be free, and those now they will lost their assembly structure, and as a result of it, the drug will be released from the cells. So this kind of thermochromic therapy is very effective for cancer treatment or that kind of purposes. So apart from these, also this kind of thermochromic materials are very useful for designing art. Especially, we can put some dynamic visual effects on the products, and also we can make dynamic paintings by using VB pen technology, using this kind of thermochromic materials. So these are the application fields. Currently, the thermochromic materials are used. But what about the recent scientific research, and how we can develop them for future directions. So here we can mostly focus on the applications of thermochromic materials to build energy efficient buildings, anti-counterfeiting technology, and energy storage devices. So how we can design this kind of energy efficient buildings with thermochromic materials? It can be done by three ways. Either you can make thermochromic coatings over the roof, or you can apply over the roof, or you can paint your building wall with the thermochromic paint. And also the most important one is the smart window. You can use thermochromic glass windows over your window panels or facade that will control the room temperature of the buildings. So among these three techniques, we here will focus on the thermochromic smart windows. So why now people are using or interested about using the smart window? Because it has many advantages. It will reduce the energy consumption. We all know that almost 40% of our energy is being used to maintain the temperature of the buildings. So by using this kind of smart window, we can reduce the energy consumption. And also we can make a temperature control inside the buildings, and it will also increase the visual comfort of the people inside. And also the most advantage of using the smart window is they are working in extreme weather conditions. They will work in winter or in rainy season also. And also we can by exploring eco-friendly thermochromic materials, we can make this smart window more sustainable for the society. So with these advantages, nowadays the smart window research is going on in a rapid mode. So how does it work? So actually, if we go into the basics of the smart window, mainly the smart window will change from colorless to color state when we expose them to the sunlight, and it will be again returned back to their colorless form when it will be winter or cloudy weather. So basically, we are blocking the NIR light in summertime, which is mainly responsible to increase the building temperature inside. So by applying this kind of thermochromic coating or thermochromic glass window, thermochromic films over the windows, we can block this NIR light, and we can only pass the visible light. So it will maintain the room temperature, as well as it will maintain the visual effects. So in case of winter season, as they will transform to the colorless and transparent form, so they will now allow both visible and NIR light. So that will eventually increase the room temperature, and also it will not compromise the visual effect. By these techniques, so this type of smart window is very effective in all weather conditions. So now, which type of thermochromic materials can be explored for developing this smart window? There are different types of materials available in the literatures based on vanadium dioxide, polymeric hydrogels, ionic liquids, perovskite, and liquid crystals. So the most used one is the semiconductor vanadium dioxide films, and they have the advantage of their reversible phase transition with temperature, and also prominent optical changes. But they have also drawbacks, like they have very high transition temperature and weak solar light absorption. Although people have tried to modify their structure by doping different elements to reduce their transition temperature, or by applying different multiple layers of titanium dioxide or silica over the vanadium dioxide films to tune their optical absorbance. Also, people have tried to make them in nanostructures, and with the help of plasmonic resonance effect, their solar modulation will be enhanced. So there are also different types of report regarding this. Now with the polymeric hydrogels. Polymeric hydrogels actually change their optical transmittance when they are exposed to the light. In case of hot summer weather, actually they disperse in water medium, so they are behaving as a transparent medium to pass through the light. But when we will heat these polymeric hydrogels, then because of the phase segregations, they will be agglomerated, and now they will scatter light. And as a result of it, their transmittance will be changed, and they will become the opaque, and they will block the light to pass through the medium. So as a result of it, and depending on the opacity of the medium, they will block the light. And that's how they work in smart windows. Very common example based on isopropyl acrylamide and polyampholides hydrogens. They have also advantages like they have reversible phase transitions and prominent optical changes. But the problems with these hydrogels are their poor mechanical strength, weak solar light modulations, and difficult to encapsulate within the aqueous medium. So in spite of different modification by implying ionic salts or solvents, or increasing mechanical strength by introducing different hydrogen bonding or supramolecular interactions inside the hydrogels, but still we have to develop a lot regarding applications of these polymeric hydrogels for smart windows. In the same way, ionic liquids and perovskite materials are also used for the smart windows, changing on their transmittance or optical absorbance. They change their colors when we apply heat, and it can be done reversibly. So these type of materials are effective for smart windows. And in case of liquid crystal, as earlier I already mentioned that liquid crystals try to arrange themselves in the presence of external stimuli. And when we put heat on these liquid crystals, then depending on the change of the solubility of the medium, then their alignment will be destroyed, and now there will be change in their refractive index, and then the transparent schematic phase will become opaque nematic phase, and they will eventually block the solar light. And if we cool down, then again this opaque state will be converted to the transparent one. So that's how this kind of liquid crystal based smart window works. But the main problem with using this kind of liquid crystals is their high transition temperature, high cost, and also the most important one, the fabrication difficulties. So in spite of these difficulties, people have used this type of materials for the smart windows, and it can be used in building different residential or commercial buildings, in making thermochromic glass in the cars, and also you can develop greenhouse to maintain control room temperature. So it can be very effective for the society. Now, apart from the smart window applications, I also like to highlight on another very interesting applications, that is anti-counterfeiting applications. Nowadays, people are more concerned about the fraud things. So we have to increase our security without compromising the quality of the things. And in this case, actually, thermochromic materials provide very very dynamic and authentication features by changing their colors. Actually, when we put different patterns or logo over the thermochromic materials, then you after certain temperature increase, then only we can detect this kind of patterns or logo. And when we again cool those, they will be returned back to the initial state. So by applying this kind of thermochromic features, we can make our materials more valuable. And people are using this kind of technology in 4 different ways. Those are you can design some thermochromic materials which will actually change their color from invisible to visible when exposed to heat or touch. And mainly thermochromic patterns or logo can be placed over any kind of surface or any kind of product. And also we can integrate thermochromic materials with holographic technology to enhance their security features of this holographic technology. And also nowadays banks are using thermochromic inks to print currency notes. And also pharmaceuticals and luxury goods are using thermochromic materials to validate the authenticity that shows color or codes after reaching certain temperatures. Also, we can combine our thermochromic materials with other techniques such as ultraviolet or infrared markers to give our systems more security. So this kind of techniques can be explored to make society more safe from being frauded. We can discuss some of the examples how this kind of thermochromic materials are working. And recently in ACS Omega, there is a report on making thermochromic inks with polyacrylamide, propane sulfonic acid, mixing with them with anthocyanidin, and here iron is behaving as a color developer. So in presence of iron, this liquid dye is changed their color from blue to brown when we apply heat, and it can be when we cool down, it can goes back to their initial blue color. So this kind of thermochromic ink is very effective. Not only the thermochromic ink, but also we can make anti-counterfeiting cloths by using thermochromic dye along with photothermal dye. Here, the group have developed this kind of thermochromic inks, where by using this photothermal dye, which actually absorb solar light in NIR region, and it will transfer heat. That heat will eventually form the colorless states of the dye to the colored one, and it can be detected with the laser with 1064 nanometers. So by using this kind of thermochromic dye and with photothermal agent, we can use anti-counterfeiting clothing designing. So apart from these two, the third one, which I mentioned, how this kind of thermochromic materials can be explored for the thermal energy storage devices. So we all know that thermal energy can be stored in 3 different ways, that is sensible, heat storage, latent heat storage, and chemical energy storage. But by applying this kind of thermochromic materials, we mainly focus on the latent heat storage, as the phase change material will absorb or release energy, and they can store the heat during this phase transition materials. So it will eventually add an extra layer to regulate an efficiency in achieving thermal energy storage devices. So it can work in 4 different ways. It can store energy or release self-regulating surfaces, and it can be explored in smart buildings and passive energy systems, and it can also be transfer heat in concentrated solar powers. So if we look into the literature, there are also different reports. One report in this journal is how they use these thermochromic materials over the battery to control their thermal management. Actually, when we apply more voltage, then the work efficiency of the battery will be decreased. But if we coat these thermochromic materials, which is composed of the liquid dye and color developer, they will change their color from colorless to different colors depending on the temperature. And when we put more voltage, then there will be change in the temperature of the surfaces of the battery, and it eventually change the color of these thermochromic patch or thermochromic films, and they will allow us not to using those high voltages. So by using this kind of thermochromic films, we can extend the battery powers or working ability. And not only the battery thermal management, also this kind of materials can be effectively used in case of firefighter protective clothing. This group have applied this kind of phase change materials with the crystal violet lactone. They will change their color from blue to colorless states, and depending on the temperature, and they have been coated inside the fire safety jackets, and they will ultimately control the body temperature of the firefighters, so that eventually that will help to control from the fire or from the outside effect. So this kind of thermochromic arrangement can be done with this kind of phase change material based thermochromic systems. Now, apart from all these applications so far I discussed, we still have to increase the efficiency of our thermochromic systems, especially in these 4 sectors, like durability of the material, cost. We have to, if we want to make them for the large scale, we have to reduce their cost, and also to increase the color intensity or increase the transparency to make them more visible, or especially in case of smart windows, and also the integration of these thermochromic materials with other energy storage or conversion systems. So these are the fields we have to carefully look after to make them more commercialized for the society. And now I like to briefly tell something about our groups. Actually, our group is working in designing different thermochromic systems, and we develop different nanostructures which ultimately change their optical properties. It will be absorption or emission, and it can be done by external stimuli such as pH, temperature, or light. And we develop different color changing films which are active with visible or ordinary light. And also we develop temperature responsive chromogenic micro nanostructures, thermally activated transparent films, or visible or NIR active arm formatting fluorescence materials. Now I like to describe briefly about some recent works with these reversible phase change materials. In this report, we have successfully designed phase change materials based switchable fluorescence materials. Depending on the solubility of the chromophore, we can tune this turn off on type of switchable fluorescence material with this phase change material. And not only that, the main problem of this phase change material, when they will change their phase, their transparency will be decreased. So we have developed different parafilm based phase change compositions, which shows very transparent uh, during their phase changes. And not only that, we also develop different ketocyanin and phase change material based microstructures, which shows colorless to color transitions, and we use successfully them for developing thermochromic inks. And very recently, also we have developed fluorescent thermoresponsive composite materials based on the phase change materials, which can be utilized for the coding and uncoding. And not only that, we have also developed parafilm and polymer thermoresponsive films that is changed from transparent to opaque depending on the weather conditions. And we have successfully controlled the inside temperature by exploring this kind of films. So this kind of phase change material based chromogenic materials are developed in our lab, and we depending on the structure or depending on the properties of those materials, we explore them either for smart window or for thermochromic in developments. So that's all from my presentation, and thank you to all of you, and especially to UNINOVA for making this INFRACHIP schools and give me the opportunity to describe about thermochromic materials and their utility. So thank you for your kind attention.
So thank you very much, Dr. Diptiman. It was really interesting talk from the part of just explaining how thermochromics work until the applications. I think was quite interesting. So we have some questions on the chat. So the first one is from Ali Azimi. He asked, are there any thermochromic materials that function in the far infrared range? So 8 to 20 micrometers and can modulate transparency similar to vanadium dioxide and ITO in the near infrared, organic or inorganic?
Actually, vanadium dioxide is an inorganic material, but mainly they have absorption in the infrared region, but it can be used for modulating this transparency, because as I already mentioned, that if we make different kind of layers with other semiconductor materials such as titanium dioxide or silicon dioxide layers over these vanadium dioxide films, then maybe we can tune more the solar light to make them more flexible for the smart windows.
So the second question is from Dr. Nizant, which is the highly used perovskite for this application?
Mainly the cesium lead halide based perovskite materials are used for these applications, but as I mentioned that perovskite have the issues with their stability. So we have to do a lot of improvement to make this kind of perovskite material stable in making films or when we expose to other medium. So that's why maybe when we can make some micro capsules or nano capsules, and we can put them inside these films. So then only we can use this kind of perovskite materials for the practical applications.
Great. And the last question, is it possible to enhance the performance of perovskites by integrating them with other thermochromic materials such vanadium dioxide?
Yes, of course, this kind of perovskite material, because we know that perovskite have very wide tunable band gap from visible to UV to IR. So yeah, effectively, these materials can be explored with mixing with other type of thermochromic materials, especially vanadium dioxide. So yeah, there is a fair scope to apply this kind of perovskite materials over this vanadium dioxide. So yeah, there is plenty of scopes to explore this field.
Thank you, Jane. I just have a question. So regarding the smart windows, you spoke a lot about the thermochromics to use on it, but also sometimes it's much simpler to use photochromic films, right?
Mhm.
So what do
Yeah,
you want to
actually,
say?
we can also use photochromic materials for smart Windows applications. But the main problem with the photochromic materials will be designing of the die. As I mentioned, that mainly the die which will change their color from one state to another, they will block this light actually. But if we consider this kind of photochromic dyes, you can see they are mostly absorbed in the UV region. So you cannot explore the whole solar spectrum by using this kind of photochromic dyes. So that's why our aim is to make thermochromic based materials, and by applying different kind of photothermal particles or photothermal structures, then we can explore the whole solar spectrum. So, and also for the photochromic materials, the stability issue will be there, because we all know that this kind of photochromic dye are very unstable with solar light. So compared to them, thermochromic materials are quite stable. Uh,
Thank you very
so
much for the clarification. So just the last question, because then we need to move on. So from Sakib Ali, what about the lead toxicity issues and water solubility of the perovskites based?
yeah, of course, this kind of issues will be there. But as I mentioned, these solubility issues can be overcome if we encapsulate these kind of perovskite materials. If we can encapsulate or making cells over these perovskite materials with different polymers or different hydrogels or other materials, then maybe you can avoid this kind of issues. So this field is very hot topic, and people are using this type of technology to improve the stability and with these perovskite materials. Yeah.
Okay. So thank you very much. It was a pleasure to have you here and have your talk. And right now, then we'll move to
Okay.
Doc.
Thank you so much, Carlos.
You're welcome.